A new scientific study has added yet another layer to the growing mystery surrounding CH₃OH Atlas. And this time, even the most conservative researchers are struggling to explain what they're seeing. For months, astronomers have watched this interstellar visitor accumulate an almost absurd list of anomalies: water levels nearly too low to measure, carbon dioxide levels far above any comet in the published literature, hints of nickel-rich material without the corresponding iron, and an early indication of non-gravitational acceleration that made some researchers uneasy. But the newest revelation eclipses all of that. A peer-reviewed study, using the power of the Atacama Large Millimeter-Submillimeter Array, has confirmed that CH₃OH Atlas is producing methanol at a level no natural object has ever shown, and not just an elevated ratio or a slightly enriched sample. This is methanol measured at concentrations so high that the researchers themselves had to abandon the standard comparison methods used for every comet before it. It's a discovery so extreme that one scientist privately described it not as high methanol, but as fuel-grade methanol. The new findings come from spectroscopy, which allows researchers to examine a comet's chemical fingerprints from millions of kilometers away. Methanol is not unknown in cometary chemistry. In our own solar system, typical comets have about 1 to 5% methanol relative to their water content. But CH₃OH Atlas immediately breaks even that simple starting point because it has almost no water to begin with. Water makes up only about 4% of its volatile emissions, a number so low that comparing methanol to water becomes meaningless. If researchers had attempted that standard calculation, the resulting ratio would have climbed into territory so absurd that no peer-reviewed journal would print it without demanding extraordinary proof. So the scientists did something unusual. They changed the reference marker. Instead of comparing methanol to water, they compared it to hydrogen cyanide, a molecule that CH₃OH Atlas does have in significant abundance. And even under this gentler comparison, the methanol levels came back with a ratio somewhere between 79 and 124. It is one of the highest methanol to HCN ratios ever recorded in any comet, asteroid, or natural body. The study authors describe these levels as enriched and unprecedented, but the numbers almost undersell the strangeness. The methanol emission is not limited to a compact region around the nucleus. Instead, part of it appears to come from an extended source on the sunward side. This suggests chemical activity not typical of natural cometary sublimation, where heating normally creates symmetric outgassing that spreads more evenly around the object. Instead, CH₃OH Atlas seems to be pushing volatile molecules outward in a directed pattern, with a chemical imbalance that stands in sharp contrast to its already unusual CO2 levels. For researchers who specialize in cometary physics, this combination is disorienting. A comet can be low in water, a comet can be rich in CO2, a comet can, on rare occasions, show elevated methanol, but all three at once, at these levels, in an interstellar object with no known formation history, forces the scientific community into unfamiliar territory. Some commentators quickly pointed to comet C2016R2 pan-stars as a precedent, because pan-stars also exhibited a high methanol-to-water ratio. But this comparison collapses under scrutiny. Pan-stars looked methanol-rich only because it was unusually water-poor. The absolute amount of methanol it produced was actually normal. In contrast, the new study on CH₃OH Atlas makes it clear that its methanol is not only high relative to water, the actual methanol quantity is extraordinary. Even when compared to a molecule as abundant as hydrogen cyanide, CH₃OH Atlas surpasses anything in the record books. It is a true methanol anomaly, not a ratio trick, not a mathematical artifact, but a raw chemical excess. Why does this matter? Because methanol isn't just a volatile molecule. It is a known industrial chemical, a compound used in fuels, energy storage systems, and propulsion experiments. Scientists have proposed methanol as a future spacecraft fuel, not just for its energy density, but for its stability in cold environments and relative ease of synthesis. Methanol can also arise from biological processes, though none have ever been confirmed beyond Earth.
To be clear, the research paper does not suggest anything artificial or biological. It sticks strictly to observational data and natural interpretations. But the concentration of methanol is so unexpectedly high that it inevitably raises questions about what kind of environment or what kind of process could create it. The authors put forward a natural possibility. 3I Atlas may have formed in an exceptionally cold zone, even colder than the Oort cloud surrounding our own solar system. The Oort cloud's temperature generally ranges from 3 to 30 Kelvin, close to the cosmic microwave background temperature of 2.7 K. The idea is that small differences in formation temperature could lead to unusual chemical abundances. But this explanation has limitations. Differences of 1 or 2 Kelvin might influence molecular retention, but they do not readily explain a dozen unrelated anomalies simultaneously: extremely low water content, extreme CO2 abundance, asymmetric outgassing patterns, metal enrichments, and now methanol levels off the scale of known natural processes. Even some of the researchers who support the cold formation hypothesis acknowledge that it is, at best, incomplete. Into this tension steps the broader scientific debate about interstellar objects and how they should be interpreted. Harvard astrophysicist Avi Loeb has long argued that scientists risk category blindness when examining interstellar visitors. In his view, comet specialists have spent decades studying solar system comets, and when a truly foreign object appears, they naturally interpret it through the only framework they know. Loeb has compared this to training an AI on a single data set. No matter what input you give it, it will force the output to match its training. Some researchers dismiss this argument, others quietly agree with it. Whatever their philosophical differences, the new methanol findings make the conversation harder to ignore. The debate intensified even further when data appeared suggesting a subtle, non-gravitational acceleration in 3I Atlas's motion. Such accelerations can occur naturally from asymmetric outgassing, but they require a specific chemical pattern that Atlas does not seem to follow, giving its low water and unusual volatile distribution. After the initial numbers were released, Loeb contacted David Farnakia at NASA's Jet Propulsion Laboratory seeking clarification. Instead of a reply, the next public update showed that NASA had revised the non-gravitational acceleration downward, altering Atlas's predicted trajectory. Before the revision, Atlas would have passed just inside Jupiter's Hill sphere, the gravitational boundary where Jupiter can capture or manipulate objects. After the revision, the predicted path moved to just outside the boundary. Both paths remain extremely close, and the change triggered speculation about why such adjustments were made and how confident scientists are in their interpretation of Atlas's behavior. The proximity to Jupiter's Hill sphere is itself unusual. Interstellar objects do not commonly pass so precisely along the gravitational edge of the largest planet in the solar system. In astrodynamics, that boundary region is not just a navigational curiosity, it is a natural zone for gravitational assists, orbital insertions, or probe deployments. If an object, natural or artificial, wanted to release smaller bodies into the Jovian system, this is exactly the corridor one would choose. Again, the scientific literature does not advocate such a scenario. But the eerie precision of the upcoming pass, combined with the chemical anomalies, makes the trajectory impossible to ignore in a comprehensive analysis. Chemical composition adds yet another wrinkle. Earlier observations indicated that 3I Atlas appears to be enriched in nickel, but strangely lacking in iron. This is the opposite of what would be expected from a typical metal-bearing natural body. Iron is abundant in cosmic dust and asteroid cores. Nickel appears alongside it, not instead of it. To produce a nickel-rich, iron-poor body naturally would require an unusually selective process, such as a collision with a metal-rich object composed predominantly of nickel. But in astrophysical reality, objects made primarily of nickel and not iron are exceedingly rare. And the idea that 3I Atlas selectively absorbed nickel while avoiding iron strains the limits of naturalistic explanations. The question lingers: why nickel, and why so little iron? Taken individually, each anomaly has a potential explanation. Low water content might come from extreme formation temperatures. High CO2 could result from chemical processes in deep interstellar ice. Non-gravitational acceleration can happen with strange outgassing dynamics. Nickel enrichment might reflect an exotic birth environment. But when all of these anomalies accumulate in a single object, and when new data continues to push them further from known natural behavior, they collectively paint a picture of something without precedent. If 3I Atlas is natural, then it represents a new class of interstellar chemistry, one that demands revised models and new theories. If it is artificial, then the methanol concentration becomes more than a chemical oddity. It becomes a potential signature. Either way, the object defies comfortable categorization. The new study does not close the mystery, it widens it. The methanol numbers are so far outside the boundaries of what astronomers expected that they force a reevaluation of every earlier assumption about this interstellar traveler.